Good afternoon, everyone.
Yes, Steve.
Yes, so Professor Molulu is having connectivity issues and he will be joining us during the talk. So I would like to ask Professor Haider if he can introduce himself and just start the talk.
Great, thank you, Steve. I understand that Umlu is having some issues with connectivity, so that is okay. I think most of you in Rwanda already know me. I have given a talk earlier as well, before COVID started. Yes. And at that time, I was really amazed by the way you were organizing this catalysis conference in a school, and you invited speakers from all over the world online, and that was, I thought, was pretty revolutionary. And then COVID appeared, and we are all doing the same thing now. So I think you were way ahead in thinking and imagining and working much ahead in time, and I must commend you for that. I've been following your activities for a while, and your group and activities are pretty international. You are inviting very good speakers and very renowned speakers, and I think we should take a clue from you guys how to organize such things. So I really appreciate your efforts, and you are bringing really good talks on this forum. I'm not as senior as the other guys, but we are trying few things at a different corner in the world, which I would like to speak about. I'm an associate professor at IIT Delhi, which is an institute in India in the capital city. It's one of the top institutes in ranking and all. So I'm thinking. Last time I talked about more on microkinetic modeling, and today I was thinking, what should I talk about? And then I thought I will talk something new on something which is now is more dear to my heart to understand what is happening in catalysis and how things are changing. And that's where I tried to write this title, which is Essential Role of the Minority Sites in Catalysis on Small Nanostructures. Okay. So this title, I think the minority is a very new word for the catalysis area. So bear with me. I would like to explain it. We already have so much discussions in the political forum on democracy. So probably that title will be clear to you what I mean from minority here in catalysis. So hope my slides are visible. I'm on the second slide now. Our group is focused on molecular modeling of catalytic reactions, and it's called renewable energy and chemicals because we are in chemical engineering department, so we have to do applied research, and we tend to apply all this theory for applications and biorenewable in a platform chemicals, so converting methane to aromatics, and we have let me put it down, laser pointer, methane to aromatics, and we also design electrodes for solid oxide fuel cells and batteries, and we do reactions like alkanes to olefins, CO2 conversion, all you can imagine. But the behind the scene is all about some theoretical work and some experimental work which are coherent with each other. And we start with DFT and mechanistic exploration. Sometimes we try to do ab-initio microkinetic modeling. And then we also have a pretty good experimental facility with all basic characterization of catalyst and even advanced one at the central facility. So we can do proof of concept experiments. And then recently we started also experimenting with machine learning and catalyst design. So some ideas which is picking up in catalysis community on machine learning, we have also tried to contribute on machine learning recently. So this is our webpage. You can browse on it and see what our activities in full. In summary, there are a few directions. As I said, we are very much interested in catalysis in complex reaction environments, especially integrating fermentation and catalysis, where biomolecules coming from fermentation of biorenewable substrates are coming. And then we try to break them down using catalyst materials to make some renewable chemicals or green chemicals you can call. And we have been quite successful in that. So a series of papers have been published over past 6-7 years. And then we have been also thinking, as I said, on machine learning. So recently we worked on thinking about new machine learning algorithms for the design of bimetallic alloys. Our thought process is very mechanistic, so I tend to call it thinking catalysis step by step. So I'm always thinking about one single step at a time, how to rationally design a catalyst surface. We have been quite active in the electrocatalytic area, so we have worked also on designing nanostructured thin film electrodes for high temperature fuel cells. Uh, and you can follow our work in the recently published in ACS Applied Materials and Nanoscale. And the work which I'm going to present today is will be at the end is recently in catalysis science and technology. So this work is also very interesting, where we are trying to see how we can convert methane directly into aromatics, so that most of this is applied, and these are some of the summary of the theme of work which is happening in our lab. Uh, let's talk about catalysis in general, how I'm seeing now molecular heterogeneous catalysis. Omulu told me that this could be a more kind of a teaching seminar. So I thought I'll keep it more introductory. If you have any issues or if you have any questions, some of you may not be in catalysis area, so feel free to ask anytime or at the end of this talk. Um, so we have catalysis is really, really interesting. And for me, like you are in Africa and a condensed matter physicist and we are chemical engineers, how do we talk to each other? And catalysis is bringing us together because both of us are doing catalysis. And that's where I say the catalysis at the interplay of science and technology. And so science is very, very deep in catalysis now. We science has a big role to play, and solid state physics, and we have statistical thermodynamics. I hope I'm audible, my voice is clear. It says internet is unstable. Hopefully I'm audible. If there is an issue, don't chat, just let me know. So there is some chats available.
You can continue. It's fine. There are just some glitches, but it's fine.
So we have statistical thermodynamics, ab-initio thermodynamics, and now we are thinking also about ab-initio kinetic modeling and in situ operando experiments. So these are very new, all of them are really new. Density functional theory maybe 20 years for now, but most of them are pretty new, and surface science is also, of course, very old, but pretty new directions in catalysis, which is leading to understand catalysis at the molecular level, how things happen at the molecular level at different sites on the catalyst materials. And this is really exciting interdisciplinary work and efforts which is happening in different departments like chemistry and physics and chemical engineering coming all together, in material science, thinking about catalysis and how to design new catalyst materials. Of course, the applications are increasing in electrocatalysis, photocatalysis, probably you name it, and there is an application for catalysis. Okay. So this is really profound for me to present it here with a different perspective, that catalysis indeed has a lot to say in the coming, whatever the requirements and research are. What is intriguing about catalysis is the multifunctional role of a catalyst materials. Catalyst doesn't need to satisfy one role. You can imagine, especially heterogeneous catalyst materials. You see, for example, we are talking about CO plus hydrogen making ethanol, for example, a simple reaction. You think about CO coming to the surface, and then CO needs to dissociate. So the same surface, and the surface needs to break the CO bond and makes carbon and oxygen species. Then you also need some of the CO to be non-dissociatively absorbed. So you need to do insertion reaction. So you have some of the CO which is dissociated, and then some of the carbon monoxide molecules should be on the surface, and then they need to be sitting next to it. Then these carbon fragments needs to hydrogenate to make methyl, and some of the CO which is non-dissociated has to insert in this methyl species, and then form these alkoxide, you can call it, and then this needs to hydrogenate, and this has to hydrogenate to make ethanol. So you can see the same catalyst surface probably, and maybe if there is a promoter, then promoter can do a different job. But same catalyst surface, for example, this reaction can be done on rhodium catalyst. The same catalyst surface has to dissociate the CO, and it has to keep some of the CO non-dissociatively to do the reaction. So imagine yourself as a rhodium catalyst, and you are thinking about CO coming to the surface, and you have to decide that some of the CO will stay intact and some of the CO will dissociate. And that is the challenge in catalysis. How you can precisely tune your surface to do this job is amazing. And nowadays you can do it. So that opportunity in catalysis is enabling a lot of research is happening in catalysis because of this opportunity. Uh, if you really see a catalyst particle, it's a really beautiful thing to see or imagine a catalyst particle. You can see that there are so many different kinds of sites available on the particle. It could be bimetallic, like I have shown you here, is the white metal is different than the black metal, and there are all different sites. You can closely imagine a cubo-octahedral shape in modeling, where there are different surfaces. For example, this is formed by 111, 100 planes, 211, and some corner sites. So you'll see that this model is resembling more or less to the this shape, which is a spherical shape, and all of these sites can play a different role. They can have different reactions happening on the surface, and that may be very exciting to explore what site is doing what and what is the critical role played by it. So let me introduce my terminology here. Now I'm calling the majority sites, which is 72%. Of course, in a democracy, if you are in higher number, you're called majority. So I'm calling majority sites. And then we have minority sites, which is 22%, let's say 100 surface. And this all depends on the surface energy. If your surface energy is low, you will probably be taking more area in a full construction of the particle. You'll be taking more area. And if your surface energy is slightly higher, then you will cover the less area, and if it is more higher, you will be lesser and lesser. So more the energy, the lesser the area you are covering on the surface. So minority sites like 100, 22%, and then you have 4%. So let's suppose for a reaction, if majority sites are active for that reaction, then you will see that the reaction is pretty much is happening on the majority side. So almost all DFT calculations, they will start with 111 surface, because they will say this is the most stable surface, and that's the view. I would say it's a pretty democratic view in catalysis, that you look for the majority, you ignore the minority, and you will do the reaction on the majority sides. That's pretty much the scene so far. However, there are certain reactions which can happen at much faster rate on the minority sites, and then you have to ignore the majority sites. You have to focus on those active sites, because majority is not that active anymore. And you have this reaction, for example, the CO bond scission is happening, or the CO bond activation, the breaking of the CO bond is happening at the step sites, which is the 211 surface of the palladium catalyst, where zinc is decorating the step sites. And we are modeling this reaction to show that the activation barriers are pretty low on these sites as compared to if you do this reaction on the 111 surface. So certain reactions, you will see the active sites are actually situated at the minority sites, and that's a different story. But if the majority is active, then pretty much the reaction happens at the majority sites. That's the point I want to make. Now, catalysis, you are a physicist, and I appreciate all your efforts. And we go back to Feynman. Feynman said in 1960 that you can do many things at the bottom. There is plenty of room at the bottom. And now you can do it by quantum confinement, by changing the size of the particles. You change the color, optical properties, electrical properties. But when we talk about catalytic properties, I would say in 1960, people are still imagining how we will do that. And now you have TEM and SEM and many other equipments. You can do it now. But at that time, it was difficult. But catalysis, people are doing it for probably 100 years before this was in the discussion. And they were changing the particle size at the nanometer scales, 2 nanometer, 3 nanometer, and they were changing the properties. And this was really, really amazing. Only recently you started seeing the changes made by changing the size of the particles or changing the shape of the particles by advanced spectroscopy. So these are very early images on gold nickel steam reforming catalysts. For example, you see the gold sitting in the black here, and that's changing the electronic environment of the nickel in the surrounding. And that's happening for 100 years, but we started seeing now that's only enabled by the advanced tool in this century, which we are seeing. For example, this one, this movie is not running, but you can see the atoms walking actually, random walk diffusion in this movie. Now, catalysis literature know this for a while. They have been changing the particle size at very sub-nanometer scale or 2 to 3 nanometers, and you will see that they change the reaction. And they have classified reactions like structure sensitive reactions, where when you change the particle size, you see a large change in the reaction rates. And then there are structure insensitive, where you don't see any change with respect to the particle size. So this is all defined in the classical textbook. And the reason for structure sensitivity, one of the reasons is that the ratio between the edge and corner atoms and the terrace atoms changes when you change the size. It's not just surface area, because you are counting or normalizing per unit surface area or per unit active sites, but the ratio of the corner and terrace and the surface sites are changing rapidly when you change the particle size, and that changes the reactivity, because your active sites are probably located, if they are located on the step sites or at the corner sites. And as you reduce the size, you will see more and more reactions happening, because the ratio is changing. And that's one of the reasons we see structure sensitivity in reactions, and some reactions are not sensitive. This is one possible reason, because reactions could be really, really tricky. For example, these are very early experiments by Sommerjoy at Berkeley, and they have shown reactions like dehydrogenations are structure insensitive. As you change the step side density, they don't change. As you do the hydrogenolysis reaction, means CC bond breaking, this reaction, and you will see that is structure sensitive, the rates is changing. And if you do this reaction on the king sites, which are the kings in the step sites, so these small defects in the step sites, and if you change that density, you will see hydrogenolysis is much more active at the king site. So these are very defined experiments telling you, and this is 1974, so in 76, very defined experiments telling, and even at that time, that the catalysis is really probing the reaction at the molecular level, and you can engineer the surface to drive reactions and the kind of reaction rates you want. So this is really very inspiring, I would say, at this age, because it was before I was born this happened. Another interesting thing in catalysis is quantum confinement, and that is the best example on this is CO oxidation reaction. For example, pioneered by the Haruto's groups in Japan, they have shown that if you change, gold is inactive, gold doesn't react in general. But if you do the reaction of gold on gold with CO oxidation, you will see as soon as you reduce the particle size of gold at 3 nanometer or 3.95 nanometer, you start seeing some turnover rates. And this goes till 2.6 or 7 nanometer. As you reduce the size further, and then you reduce it further, and you see a large drop and change again. So only in this region from 2.5 to 3.5, the cluster is active. And this is really, really inspiring. People have worked a lot on this reaction. Recently, I would say my friend at UCL has shown, for example, that only if these are few clusters of gold on Syria, and you will see that the only difference may be 1 atom or 2 atom on these clusters of gold, and some are active and some are not active. So even adding 1 or 2 atoms in a cluster of gold on the surface can change the reaction rate. So this is really exciting, that you can get these quantum confinement at the nanoscale level, and show that catalysis has a possibility of doing real nanotechnology, I would say, not just the size effects or surface area effects, but real quantum confinement. And catalysis in that sense is really exciting. Now let me talk about some of our work. So we have talked about particle size effects, but what is more intriguing in catalysis is particle shape effects, because now with the advancement in chemistry synthesis protocols, and you can synthesize materials in certain shapes. You don't need to be spherical. For example, our collaborators at NCL Pune can make these cubic particles, which are palladium cubes, about 22 nanometer. And they can also make this octahedra particles, which are like this. And these are only 111 surface, and these cubes are 100. As you can imagine, if you're making a cube, you only are exposing the 100 surface, while octahedra is exposing the 111 surface. And then there is a spherical particle, you can imagine, which can have both 100 and 111. Going back to our discussion, terminology, where I said that the 111 is majority, is about 72%, and minority is 100. But you can now probably dissect it. You can make a particle which has only minority sites, and you can also make a particle which has only majority sites, 111. And you can do this reaction. You can do reactions on them. Once you synthesize it, good for the reactions. You can do experiment with them. And we did this experiments on phenol hydrogenation, phenol going to cyclohexanol and phenol going to cyclohexanone. So these are the two possible products. If you hydrogenate cyclohexanone further, you get cyclohexanol. So cyclohexanone is the product in the middle, and then you go further down the road or hydrogenation to make cyclohexanol. Okay. Now look at this. If you make cyclohexanone, from here you open up the path for adipic acid and nylon. So it's a commercially relevant reaction. It's industrially important reactions. And recent work by Liu has shown that you can do this reaction on palladium catalyst with 99% conversion and selectivity at 50 degrees centigrade. So almost at room temperature. So this is really exciting. Many people have studied. You go up to cyclohexanone, you don't make cyclohexanol, and then from here you go all the way to chemicals. And this is, we can think about what facets, where this reaction is happening, what is the active sites. We try to start understanding this reaction on palladium cubes at 22 nanometer, and you do this reaction on cubes, and you keep scratching your head, and what is the product, and you keep thinking. Then you do this reaction on octahedra particle, and you scratch your head again, what is the product, and here is the answer. Okay, on cubes, you will pretty much see at the end of the reaction is cyclohexanone. On octahedra, which is 111 sites, the majority sites, you will see cyclohexanol. So on cubes, you start with the reaction, and you will see till the end of 40 hours in the reaction, you still have cyclohexanol, about 90%. Cyclohexanol is formed, but less than 10%. Here, the reactivity trends is different. You start with cyclohexanone, but most of the cyclohexanone is converted to cyclohexanol, and you pick up the trend here directly to make cyclohexanol at 40 hours of the reaction. Conversion is absolute, almost 100% in this reaction, because as I said, at very low temperature, you reach very high conversion. So this is absolute conversion, okay? If you think about spheres, which has majority 111 and minority 100, you go back and you think 100 was making cyclohexanone and 111 was making cyclohexanol. So what is a combination of these two, which is the spherical particle, is going to make? And the answer is, if you have these supported on titania, the palladium sphere, which is the real catalyst, a spherical particle, you do this reaction, you will see initially it will hold up to cyclohexanone. But then this selectivity will die. This is different than here. Here, this dies rapidly. But here, it is dying, it will hold up for some time, and then it will die, the cyclohexanone, and then this cyclohexanol will pick up, and that will go to 100%. So this is exactly the same what we saw on 111. So majority dictates the selectivity till the end of the reaction at for 25 hours. We are doing this reaction. But for me, what is more interesting is the initial period when we see that the initial selectivity trend PD100 sites, which is the minority sites on a spherical particle, is dictating some trend. And that is where there is a major role or an essential role played by the minority sites, okay? And we thought about exploring the reason why these minority sites could play some role in dictating the selectivity. Most of the time, when you're looking at the end of the reaction, you are thinking about the majority sites, and pretty much you can do your modeling on the majority sites, which is the 111. But if you're thinking about reaction and you're thinking about the initial phase, and initial data could be skewed, and that's where I'm talking about, that you will see that this is the phase where the minority sites are playing some role here in dictating the selectivity, and that's something to explore. And the reason for here is this. If you see the binding of phenol on the two surfaces, 111 and 100, you will see the 111 sides, the binding is about minus 102 kilojoule per mole. On the 100, which is the minority sites, is about minus 135 kilojoule per mole. Most of the carbon is sitting in sigma bonded adsorption geometry, while here it is more pi bonded and less binding. So you have less binding, it's shared. One palladium atom is shared by two carbons here. Here, one palladium is sitting on one carbon is sitting on single palladium. So it's much more tighter bonding. So what you are seeing here is, because of these binding differences, you have much higher binding here. So the minority sites, while they are less in number, they are more reactive because they provide much better binding site for the reactant. And that is the reason why that holds up. So where is the selectivity decided? The selectivity is decided because as you increase the coverages, this binding mode can also change. And and the 100 surface, which is much more tighter bonding, can slowly change to something which is pi bonding mode and will be similar to palladium 111. We have done some D band analysis on that and can explain it, how the D band is moving, how the coverages lead to similar binding. So that is one reason. The other reason for selectivity change is the facet dependent selectivity control. If you look for the product cyclohexanone, on 100, it is much more difficult to hydrogenate it further to make cyclohexanol. On 111, it is much more easier. Here, the activation energy is 101 kilojoule per mole, and here the activation energy is 57 kilojoule per mole. So combining all of these reasons explain the binding is much more stronger on 100. Then we say there is a shift, and then also cyclohexanone is much difficult to hydrogenate on 100 as compared to 111. That's what we see in the final selectivity trend, that initially it holds up, but later on it can tend to die because 111 will start producing so much of cyclohexanone, whatever is coming even from the minority sites will go into the majority sites, react and form cyclohexanol. And that's what we see in the experiment. So the initial hold up by the minority sites loses its trend because the majority kicks in. Okay, so this is slightly convincing, tells us that there is a role in catalysis for minority species, but not so convincing. So let me go to another example where there is an importance of a metastable species in catalysis. And this is not metal, I'm talking about metal carbide clusters on the zeolite catalyst, which is really an interesting case in catalysis. We discussed the metal case. Now we are going for nanostructures, which are metal carbide structures, and how they play a role, and especially the metastable species. We are discussing about a new reaction, which is methane dehydroaromatization reaction. This reaction is you take 6 molecules of methane, go all the way to benzene, and you will make 9 hydrogen molecules. So you need C6. So it is directly dehydroaromatizing without any oxygen, non-oxidative process. And if you look at the delta G for the reaction is not very spontaneous at room temperature, and delta H is endothermic. So you require a very high temperature to do this reaction, and temperatures are about 700 degrees centigrade. I wrote it wrong, 973 of Kelvin. Okay, so 973 Kelvin. And you see that as soon as you start the reaction, maybe initially you will see less selectivity, but sooner or later you will be seeing very high selectivity for benzene. So you get up to 80 to 90% selectivity for benzene. However, the conversion in this reaction is a worry. You hardly get 10, 12 maximum percent conversion in this reaction. Here it is showing 7%, but you get a lot of selectivity. And imagine if you can do it and you can regenerate the catalyst and you can do it in a cyclic operation, you can drive the conversion. And that will be one way to upgrade natural gas into aromatics. And that's a very holy grail problem in the natural gas research, that you can convert natural gas to something really valuable. And this is one way. The problem here in this whole reaction and in commercialization, I would say, is that one I highlighted already, the low conversion. And the other problem is the catalyst deactivation. Slowly, you will see the catalyst deactivates, it will form a lot of coke, and then you have to regenerate it. The major problem is the deactivation. Okay. Now, what is the catalyst and reaction mechanism? The catalyst is bifunctional. Some authors have also debated that this could also be monofunctional. So I don't know what to call at this moment, but I would say it's bifunctional, but some authors have debated monofunctional as well. This is molybdenum metal sitting on SgSm5, which is the zeolite. Sometimes some other zeolites are also used, but predominantly and most important catalyst is MOHZSM5. If you look at the reaction, it starts with methane in the gas phase. You have to activate the first CH bond, and you make CH3 star species on the catalyst surface. And once you activate it, you may activate another methane molecule, and then you have another CH3. You have to do the CH3 coupling reaction. So you make CH3 star species. You can do 2 CH bond activation. You can do CH2, but you have to do somewhere CC coupling. And from here, you can do another. From these ethane, you can do another CH bond activation to make ethylene. And from ethylene, you can make another CH bond activation to acetylene. There are debates in the literature whether ethylene is the product or acetylene is the product, is the main intermediate or on the moly sites. This entire reaction
the CH bond activation and CC coupling steps are entirely governed by the moly sites, the molybdenum. If you don't have molybdenum, you won't get this product. Okay, so you need the metal here. Okay, and whether it will stop at ethylene on the metal side, we don't know, or whether it will go all the way to acetylene. There are some recent experimental work and kinetic studies that people are saying acetylene is the key intermediate, but we leave this debate here. Irrespective of ethylene or acetylene, there has to be some aromatization happening at the Bronsted acidic sites. This could be exactly at the metal zeolite interface, or maybe far located on the zeolite surface. Doesn't matter, it can diffuse and go onto the zeolite sites where it can form the aromatized products. This chemistry is known, so these ethylene or acetylene can aromatize on the zeolite catalyst to make benzene, and that's the reaction chemistry. We will focus predominantly on this chemistry because that is done by the metal, but aromatization is known, so we are leaving for now that this is understood already. Okay. Now bifunctional or monofunctional, depending if it goes completely away from the metal side, goes to the zeolite surface and does this reaction, then maybe monofunctional, bifunctional. And if it is happening right at the metal site, at the zeolite interface, everything, all the aromatization is also happening right there, then it may be monofunctional. And this may be a decision you have to decide from your experiments and debate maybe with others. Okay. If you look at for the species sitting on the catalyst surface, so you have moly oxide. So you will start with the reaction catalyst structure, which is moly oxide. So when you're making the catalyst, you calcine the catalyst, you always get moly oxide catalyst. Okay, so this is moly calcine catalyst is moly oxide. So you can see the Zane's spectra of moly oxide crystals, and the calcined MOHZSM5 resembles pretty much the same as the oxide. So you need to generate the active sites. Moly oxide is not active for this reaction. It won't do methane dehydroaromatization. You need to really generate this active site. How do you do that? You have to run this reaction in methane for 1 hour. So you run this and you have to treat the catalyst in the same reactant methane. And then you will see that these shifts are shifting, and then you may run it for longer, 12 hours. You see it's shifted again. And what are these peaks correspond to? These peaks correspond to a moly carbide species. So it's MO2C powder. So they're exactly coming with moly carbide. So what you're seeing is what was moly oxide in the beginning. Once you carbonize it, you make your catalyst as a moly carbide. And this is not metal, so metal is in the background. You see these peaks doesn't correspond to the metal, so you don't reach to the pure metallic phase, but you make carbide species. So all of these moly, which is sitting on double aluminum side, single aluminum side, and double silica sites on the zeolite surface, are all transformed into carbide species. Okay. Now, the holy grail of this research is about starting with moly oxide. You have moly oxycarbide. So all of these oxide is changing to carbide. So you start with moly +6 and you are reducing the catalyst in methane environment. You make moly carbide, or maybe moly oxycarbide because still oxygen is there. And then you make pure moly carbide. And then this is sitting on the aluminum side, double alumina side. Then you transform it. So the moly carbide species starts moving to single alumina sites. They can also move to double silica sites, and it keeps reducing. So somewhere in this region, you generate benzene, which is, and there are experimental studies, operando FTIR studies by Israel Wax groups. I have seen really good XAFs and X-ray absorption spectroscopy studies from Europe, and many studies have assigned one of these species, either oxycarbide, some of the recent studies, or this carbide species with the dehydroaromatized product, which is benzene. However, they don't stay here. Since the methane is passing, methane is a reactant, it keeps evolving and it goes all the way to double silica site, and that's where you will lose the reactivity of the catalyst. And then these sites will be transformed into a moly carbide nanoclusters. They will grow on the surface in large clusters, and these are large nanoparticles, and they will form outside the zeolite surface, and that will result in a lot of coking, and that is the state of the art. We don't know what is the exact site, But we know at least that the methane, benzene is generated when the species are kept in oxide or oxycarbide or carbide form. But as soon as you grow large particle outside the zeolite surface, you start deactivating your catalyst. So this is the scenario. You start with the species inside on the double alumina or single alumina sites, and then they migrate, go all the way outside the catalyst where there is no alumina present, there is mostly silica, and you start growing larger nanoparticles of these moly-carbide, and that deactivates it. Okay, I show it here again. You can see that it starts from the inside channel. Inside channel, as long as it is there, methane is forming benzene. But as soon as it goes outside, you start having coking. And this is showing also in the movie. You can see inside the channel, there are small clusters. And when they come out, they start coking and make larger clusters of nanoparticles. And that's really deactivating the catalyst. So this is what you want to avoid. Now you think about experiments. We have thought about how, if you have this molecular level information, what is the key? That somehow you generate these active sites and you keep it right there. You don't let it go outside and make these nanoparticles. Somehow you can control it right there. And that's the idea. If you have these sites right there, you try to stop them go all the way in this molecular form, and you don't let them grow. And you make them stable. And there could be multiple ways you can try. You can do moderation of support acidity. You can change the acidity of the support. You can change metal precursors, which are used to make molyoxide species on the surface, so that you can change and stabilize them. Or you can change the carbonization protocol, or you can add a promoter which can stabilize these species. All of these combinations, essentially almost everything tried in the experiments to make this catalyst stable, can be pinpointed exactly on how you are actually anchoring these species on the surface and how you are regenerating it. And that is really, really amazing to see that at the molecular level, you have a tool to control the active sites by different experimental techniques. And the moment you are able to control it, you can control the stability and activity of this catalyst. I will show you one example or maybe 3 examples, like moderation of support acidity, where you can treat it with boric acid treatment. And you see that with BA treatment of MOSGSM5, sorry, I misprinted, I wrote it wrong, at ZSM5. And that you see that pretty high benzene formation rate at 70 or 80 minutes. The reason for that is the moly oxide species are much better anchored on these BA treated MOSGSM5 as compared to the pure MOSGSM5 catalyst. And the resultant BA treated MOSGSM5 produces less coke as compared to the main catalyst, because the reason that is that you have much more anchored MO oxygen species that leads to better carbide species, and then you get much better reactivity. Since this presentation is more on the theory, I will skip down more experiments, but we tried almost all of this, which I'm discussing, all of these arrangements, and we can control or maybe produce or maybe anchor better these species inside this the zeolite pores, so that we get better reactivity and better stability. One is the metal precursors and also carbonization conditions. I'll skip it with the interest of time. I will talk more about on this active site, and this is really, really interesting and intriguing for me, because if you look at the active sites itself, these are very small nanoclusters. Okay, as soon as you make bigger nanoparticles, they tend to die, and you have to keep them inside the zeolite cage, inside them. You don't want to you don't want them to migrate outside and come outside. So you want to stop it right there. And there is a debate on the exact structure of these small clusters. For example, Israel Wax groups, and there are 2 very prominent work which I'm highlighting here. They have said that the structure may be MO4C2 type of a species. So the primary structure is MO2 and C, and Vecchiusen group and Bale and Vecchiusen group, they have said, no, this is MOC3 species. So if you want to make a cluster, the cluster could be MO2C6. So there are 2 different parallel views. Now people have also come up that it's not just carbide, it could be an oxycarbide. And what is the structure of the oxycarbide? And as I said, the holy grail in this rework is exactly what I'm talking about: oxycarbide, carbide, and it could be alumina supported on the single alumina or on the double alumina. And all of this can be debated, what is the exact form here. And that's I have left it open. That's why these bonds are left open, because we don't know exactly what is the exact structure of these species, and that can be debated. You can write another paper or exactly on debating that this is not this and this is the one it is. Uh, as I said, these both structures are interesting, and we did a really detailed DFT studies, starting from methane, first CH bond activation, then second CH, then we have CH3 coupling reactions, then hydrogen transfer, then another CH bond activation, making all the way to ethylene. We thought at that time ethylene is the key intermediate. From there, it will aromatize to make benzene. And you will see most of these CH bond activation barriers are pretty high, 116, 151, 90, 70, 95. And we do a comparison between MO4C2 and MO2C6, the two clusters. And we study the first CH4 has to do CH bond activation, make CH3. Another CH4 has to come in the vicinity. You see pretty high barriers. And we also change the charge on the cluster because the support will change. Some have the charge effect. So we started with neutral. We did also +1 charge. We also kept changing the charge in much more detailed manner. And we saw that the barriers are pretty high. And it remains inconclusive which one is more active. Okay, well, so the two groups are debating from two different experimental view, and we as a theoretical understanding, we are debating, and we are not able to understand or pinpoint exactly which one, because CH bond activation is still a challenge in almost all of these clusters. It doesn't matter whether you keep them charged or neutral, whether there is a support effect or not, it's still a big challenge. Okay. So we think, what is the answer? So we started exploring the two units here which we have taken are the lowest energy structures. So we always start catalysis, as I said. If you are in the lowest energy structure, if that is the active site, most of the reaction will happen on that lowest energy structure. We thought that now maybe is the time to think about a metastable structure. And this is the most stable, where we did this reaction of MO2C6 in the previous slide. And then we thought, okay, can we find and identify a metastable structure, an isomer of MO2C6? And this is probably an isomer. You can see is the same formula, but then you have slightly different geometry. And can this be more reactive? And this we obtained from a cascade genetic algorithm search from FHI AIMS software. And that we did, it has some unique operations through which we were able to identify this structure is about 16 kilojoule per mole higher in energy, depending upon the core. Some codes were giving only the difference is about 6-7 kilojoule per mole. So it's still slightly higher. It's not very high, I would say. And we can see in the 50 kilojoule per mole window, we have identified actually 5, but this one was really, really interesting, which is the metastable, which is 16 kilojoule per mole. So I'm calling the lowest energy structure as the most stable structure. And this one is the metastable form, which is shown here. So both these structures are in front of you, and we will compare. So now we will do methane activation, or the CH bond activation of methane on these most stable species, and also on the metastable active sites, and we'll see what is the results. If you see and compare the Gibbs free energy barriers of methane activation on these clusters, you'll be really, really amazed to see that the most stable form for the same CH bond activation, the barrier is 95 kilojoule per mole, while on the metastable form is about 46, nearly half of it. And you will see the reaction energy is also becoming more and more exothermic as you go to the metastable form, and that is much more facilitated CH bond activation on these clusters. We thought maybe it's a fluke, maybe our methods are wrong, something is probably not working, but let's explore what is happening, this CH bond activation, and why is that so? So we thought, okay, let's try to understand the transition state, and that is where we observe a very unique phenomena, which is a proton-coupled electron transfer, which is very unique in heterogeneous catalysis. It happens a lot in homogeneous, but and enzyme catalysis, but proton-coupled electron transfer is always unique in heterogeneous systems. So this is one 4-electron transfer, and this is pretty much linear. You can see it comes in one plane, and you will see that leads to a much better orbital overlap. And the more it will become 180 degree, the better overlap of orbitals will be there, and that will facilitate. So there is a geometry of this cluster which is facilitating the CH bond activation on the metastable form. And that's the reason why it is coming to 46 kilojoule per mole. We did a very detailed geometric analysis and quasi-restricted orbital analysis. And we did this, all of this, and we can see here that on the lowest energy structure, which is the most stable, the angle is about 153 degree, as I said, in the geometry, but here it is 177. So it becomes more linear. That leads to better overlap. You can see here it is 13%, and here it is coming to 22%, and here it is 37%, it's coming to 40%. So this is really enabling from the electron transfer and also the proton transfer steps, the better overlaps in the metastable clusters is resulting to much more facile CH bond activation. This is much easier as compared to the other geometries which we have studied so far. This led us to really assess the role of the metastable clusters in such catalysis, which has not been studied before. People were always thinking about the lowest energy structure, and that's all I need to care about. But let's suppose I see the 5 structures like 0, 31, 45, 16, 42, and these are of different energies. I can do a Boltzmann probability distribution of these, and you can see the first one is about 0.85, so the lowest energy is much more populated. Then metastable still has some population, about 0.1, and rest of them are much higher energy, so they don't appear in population actually. But if you really look at the rate constants and you do methane activation and all of them, rest of them have much higher energy, so they won't contribute. But the metastable has much lower energy, which is about 46 kilojoule per mole, as I said. That is going to play a much bigger role, and that's where you need to estimate. You need to write and think about an ensemble average representation of the rate constant, and that's slightly different. The way we have always thought the rate constant is the rate of the reaction on the most stable surface, but now we can express an ensemble average expression for the rate constant, and we can see the contribution of the rate arising from the metastable species in the overall rate constant. So if you're writing the ensemble average rate constant for all these 5 species and you assess for metastable species, you will see it's pretty high. It could be K contributed, could be absolute to unity. So that is really I'm pointing out. Now I'm not saying that the entire reaction is dictated by the metastable species. Still, you have so many steps. This is a much more complicated reaction. As I said from the beginning, you start with first CH bond activation, then you have a CC coupling, then you have another CH, then you go for another CH activation, then you have another CH activation, and you have to do aromatization. So, but at least in one step, I am showing you that from an ensemble average representation, the metastable species are much better than the lowest energy structure, and they have a role to play in determining the rates. Okay, so this is my one thought. Now let's see what is happening on ethane. Interestingly, when we do the ethane, the CH bond activation in ethane, you see a similar effect, exactly the same, nearly half. On the most stable, it's 97 kilojoule per mole, and the metastable is about 47 kilojoule per mole. The reaction is becoming more and more exothermic on the metastable species as compared to the most stable cluster geometry. And that's again can be explained from a QRO and geometric analysis. Here you have 150 degree on the most stable, on the metastable is about 179 degree, nearly planar, much better overlap. Here you have 21% and you have 50% much higher than the one which is on the lowest energy structure. So that is facilitating the CH bond activation. You look at ethylene. So we started with methane, ethane. Then if you make the intermediate acetylene, you need to do CH bond activation of ethylene on this reaction. And you see the same effect on ethylene. CH bond activation is much more facilitated, starting from 161 kilojoule per mole. On most stable, it is coming to the metastable, which is about 82 kilojoule per mole, nearly half. And it's becoming more and more exothermic. This was slightly endothermic, but this is becoming more and more exothermic. And all of these barriers, everything follows a BEP relationship, so it's all consistent. If you don't believe me, this can also be explained from the same geometry or orbital analysis point of view. But if you don't believe me, you can try different functionals. You can fix the nanocluster, relax the nanoclusters. I have shown you results which are delta G values, but you can rely purely on the DFT values. And you will see the trend is pretty much consistent, whether it's CH bond activation, methane, ethane, ethylene. On the most stable, if it is 127, it will come down to 68, it's nearly half, 142 to 70, 151 to 91. You see on the relaxed nanocluster, same trend, 119 to 61, 120 to 65, 161 to 95, nearly half in all cases. And I showed you the delta G value, which is at the room temperature. And you will see that nearly in all cases, we are reducing the barrier on the metastable species for CH bond activation, whether it is in methane, ethane, and ethylene, irrespective of the functional used, irrespective of the geometry, you are reducing the energies. And that is really exciting about metastable species for us, at least. Now let's look at finally the ensemble average representation of the rate constant. If you just judge between, because the rest of the cluster in higher energy, you can ignore them because they have much higher CH bond activation, but just play around the metastable and the most stable. And just look at the metastable one. And you can write again the Boltzmann probability distribution, and you can write what is the contribution in the rate constant coming out from metastable species. You will see their population is about, if you're just seeing the two cluster, ignoring the rest of the others. If you see more, probably this distribution will be slightly lower, uh, about 0.24. And from this probability or population, I would say they have a much more to contribute. And you will see for CH bond activation in methane, ethane, and ethylene, they contribute a lot. And that's nearly unity, about 0.99. So that is where we have to think and scratch your head that maybe our representation of the most stable surfaces or active sites has to acknowledge also an essential role played by the metastable species. I don't have the final answer because we don't have the complete picture of the reaction, that what will be the reaction rate or overall turnover rates on the entire metastable species anchored on the zeolites versus the most stable species on the zeolite. We don't have the complete picture and answer, but we have some clue and some answers. And we also saw some clue and some answers in the palladium case, where we have seen phenol hydrogenation, where the initial rates were dictated by. So there are some regions of hope where metastable or minority sites, which are less populated, less in number, are playing an essential role. So I don't think I have courage enough to write more conclusions at this forum, but since it's a politically charged environment worldwide, I would say in catalysis, at least, uh, unlike democracy, I would say minority sites could play an important role in making decisions. So that probably is a good point to leave you scratching your head and thinking and imagining catalysis or the surfaces, how things are happening, and imagining also about the sites which may not be highly populated, but they might be playing some role and an important role. So this is where I'll leave your imagination. I would like to acknowledge some of my collaborators here at NCL Pune. Professor Vinod did experiments on the phenol, especially on PD nanostructures he made. At IIT Delhi, Professor Pant is doing experiments with us on methane dehydroedematization. Professor Shashwat did the genetic algorithm search with FHI claims. So he gave us the metastable clusters, and Shikha is a student now, a doctor actually, Dr. Shikha Saini. And IIT Roorkee Professor Puneet is doing some really developing very deep understanding for us in understanding what is the reason for very facile CH bond activation. All of this work is primarily done by Sonit Baryan on methane dehydroaromatization. Professor Shalaka did this work during her PhD on phenol. Saurabh is doing great work on methane, experiments on methane. And Tuhin Subra Khan is leading the theory side on all of these efforts in phenol and as well as on methane activation. I put down Sheikh Hassan again, but Shikha is part of this group. So thank you very much. I acknowledge also our high performance computing facility and also our funding from Gas Authority of India Limited, which is responsible for methane work. Thank you. Any questions?
Thank you, Professor Haider, for this interesting talk. So I guess we'll go now to the question, and we start to have some question on the chat. I guess you can see some of them, but I will just repeat them for the recording. So the first one is from Omololo Akinojo. He asks, can we also include structures around metastable sites? That is, slight differences from the metastable structure?
So as I said, we think that there has to be more actually. So we started with two structures and we kept focusing on that. But if we really explore, all of them are really exciting. So we got two structures. Yeah, this one. But we just focused on these two, but we have to actually explore all of these structures because maybe some are good in CC coupling reactions. Some are good in CH bond activation. Some are good in hydrogen transfer reactions. Some are good probably at the interface. And that will be a much more detailed and comprehensive study if we look for the entire catalytic cycle on other structures as well. So this is important. This is just a beginning. But if you really look for the entire cycle of reaction, and probably you have to explore. Maybe you are lucky. Maybe most of them are showing much higher barriers, so you won't get anything. But it's about being lucky. If you get something, then you will start thinking. And I doubt, because in the entire literature, many different operando and many good studies with good spectroscopy, people have identified different species. So some are talking about carbide, different structures, oxycarbides, and they can't probe at this level the exact structure. But that gives you a clue that probably not just one site, maybe more sites are involved in this reaction, probably, yeah. So that's the right time to think about an ensemble average.
Okay. Yes. I have a question myself. Like in your talk, you mentioned most of your work, but you said very little about the computational technique that you were using. Like, if it's simply a DFT calculation, how do you run those calculations? What are the specificities of your calculation, for instance?
Mm-hmm. So we tried different softwares. We tried different functionals, as I said. So I understand the condensed matter physicists even do much higher order functionals, but these are pretty well accepted. So we started with RPBE. Some of the other calculations were with PW91 also. So I would say, let me close down. So this one I'm showing you RPBE and V3lib. And this one, two different packages. This is DMOL 3 and this is pretty much is ORSA package. And then we also used FHI AIMS for some energy calculations. So three different packages we tried and different levels of energy convergence. More values are there in the paper. Which is, I think, will appear hopefully in RSC nanoscale. So you'll see it soon. So we tried different things. We also tried whether the cluster will stay fixed or can also relax the coordinates of the cluster. So I'm showing you three different ranges. Of course, it's debatable that you can go for even higher level of theory to really pinpoint exactly what's happening. But I think this is enough for us to see the trend that pretty much we are getting half activation energies. Yeah.
Okay. Another question from the chat from Christian Jumet.
Yes.
And he's wondering whether catalysis reaction is linked to electrophilicity and softness of the system.
I still don't get it. What is it?
Whether the catalysis reaction is linked to the electrophilicity and the softness of the system, or
I really don't get the question. What is electrophilicity? Yeah.
Yeah.
So there is some charge transfer. So we have not correlated the whole thing with the charges on the clusters. That's the direct correlation. We could not find direct correlation from the charges, the CH bond activation. So that's why we did the orbital analysis. If that is the question you are asking. So if electrophilicity is defined more like I would say organic reactions we hear about. It's more on the heterogeneous surface, so it's more correlating with the charge transfer. And we could not find a correlation here for all the CH bond activation with respect to charge transfer. So that's why we did the orbital analysis. We could not find a correlation. Maybe there exists a correlation that the charges correlate.
I have another question. So in your introduction, it's not completely linked to this talk, but in your introduction, when you mentioned the type of work you do in your lab, you talk about machine learning.
Yes.
What type of research do you do in that specific area?
So this we published this year in the beginning, and we started with more work. One PhD student is working in that area. We started exploring. This work came out in JMCA in 2020. I think this year is wrong. It's actually
Okay.
so what we are trying to do is how do you design bimetallic alloys or single atom alloys? Because you have transition metal surfaces, which one to mix and how you mix it. So how do you predict binding energies? And from there, build up your microkinetic models. So that is what we're trying from machine learning approaches. We have tried different methods, but gradient boosting regression algorithms are, or the tree-based algorithms are so far in our thinking is effective. So that's where we have started a lead. I'm at this moment, many people are trying different methods. There's a lot of questions on the methods itself. Those who are familiar with much more deeper methods, they can try that. We are thinking whether that can be applied directly to catalysis. So if you are doing a microkinetic modeling, can you use those values coming from an ML algorithms, predicted from an ML algorithm to build some microkinetic model? So I encourage you to read this paper. I don't have slides now to show any results. Yeah.
Another question from Parveen Rawal. A question from Parveen Rawal. How can we approach to the idea of a metastable species for a particular cluster?
So you have to just expand your view. I would say that sometimes you just look for what is the lowest energy structure, and then you do your reactions or calculations on the lowest energy structure. But you have to expand your view. Now, I have seen some genetic algorithm based searches for clusters, and that they never get those the exact metastable ones. So we tried, especially with the FHI AIM softwares with my collaborator Shashwat. He was able to find some unique structures which were not visible in the other algorithm. So somehow the algorithm was working in finding us new structures. And in that sense, we were lucky to find that one, which is more looking really, because it's a geometry of the cluster which is enabling much better CH bond activation. So you have to keep looking, you have to expand your view. You need better algorithms in cluster searches, which are ab initio level algorithms, because if you look for general GA search or neural network based algorithms, they don't understand the ab initio level. So you might have to explore, or you might have to develop algorithms which can do search at the ab initio level. So that is one way, I think, and they probably can find more structures. Yeah. But I really don't have a clue that if you hit in this direction, you will get the cluster. I don't really know. Yeah.
So there is another question from Christian Germain,
Yes.
and he was asking, to be shown the stability of a functionalized system, is it better to compute the binding energy by the energy of each radicals or the energy of formation?
I could not get it. What was that from the?
Yeah, he's interested in knowing about how to study the stability of a functionalized system.
We don't study the radical. We start with the heterogeneous. Is the gas phase species has to come and absorb on the catalyst surface. Okay. So organic systems and other systems, organometallic maybe, but in heterogeneous is the gas phase species has to come to the surface and bind, and that is where we start the binding. Now, binding has to be follow the Sabatier principle, so it should not be too strong or it should not be too weak. Otherwise, you won't get the reactivity. Either it will cover the surface or it won't come and see the surface. So you need to have somewhere optimum binding where you see exactly the kind of binding which will drive the reaction. Does that answer you? Yeah. It's not very clear.
Yes. So one more, an additional question about the metastability of the system. Am I right when you understand the metastability is more or less about the orientation of the cluster? It has nothing to do maybe with excited states of the system on its own in a specific, let's say, specific configuration.
So that was one question we thought we will explore, and we haven't explored it yet. It's the excited states, you know.
Yeah.
And, we have to see that. We have no answer yet. We thought about doing this, okay. And we thought, but we haven't done it yet. We're not. I think that's an important question, but we need to see that also in metastability. Yeah.
Okay. So I guess there are no other questions on the chat for now, at least. Uh, okay. There is one more
One
that
more.
I just received. So it's asked how one can control the metastable structures experimentally as they are less stable. They won't
Yes.
stay in reaction for a longer time.
So experimentally, you don't control anything. They exist because of the Boltzmann probability distribution, and this reaction is happening at 700 degrees centigrade. Now, Philip Sauté's group and many other groups have proposed that if you are at 400, 500 degrees centigrade reaction and any other species exist 100 kilojoule per mole higher in energy, that may be accessible at the reaction temperature. So some of the maybe it's like 200 kilojoule per mole away, so then that may not be accessible at reaction temperature. But if you're running the reaction at 700 degrees centigrade, so all of these species are available for reaction. So if a methane is coming, it will not just react with the most stable, it will also react on the metastable. However, metastable is lower in number, which is the minority. Now, I don't have a way, but you can try. I showed you a few experimental ways. Maybe somehow you can restrict the most stable structure, but that may be not possible at the molecular level. You hope that the reaction condition will make it feasible to do this reaction on the metastable species.
Is it any way to control it, maybe with a laser or some light
Other
source?
no, catalysis won't work that way. So that preciseness won't come in catalysis or industrial catalysis. The one way I can imagine is you add a promoter or you change with the support, and in those supports maybe the metastable species or the structure become most stable, and then it will be, if you're lucky, and then in that case like let's suppose I'm doing this cluster which is away from the support, but once I anchor them on two clusters, the energies will change, and then the metastable may become on one type of support maybe more stable than that, and metastable is already, because of its geometry, it's activating the CH bond, and in that case, hypothetical case, it may be able to do that. Yeah. So once you anchor them on different support, their energies will change. Yeah.
So I guess there are no more questions. I would like to thank you, Professor Haider, for this very interesting talk, and we hope to have you with us in the next few months, hopefully.
Thank you.
For another talk or maybe in person. So you'll be welcome to come and meet us
I
at
am looking forward for that. And one day, right now it's COVID, so we don't know. But at some point, it will be nice to visit Africa. I have a very deep respect for the African culture. So someday, one day we will visit. And you are also welcome, all the students and researchers at your institute. We are very much open, and anytime we are located next to the airport, so it's very easy to come. So please visit. Yeah. And we have a program, international students program at IIT Delhi. So students can also do PhD and higher studies here or a postdoc here. Yeah.
Yeah, I saw you gave the link of your website. So I guess if anyone wants to get in touch with you, it's also possible through your website. So thank you again. Thank you very much for this talk, and we'll stop the recording now.
Thank you. Appreciate your time.
Thank you.
Thanks for your patience. Thank you.
Thank you.